knows a lot about the science stuff. Professor Dave explains.
Cross-coupling reactions forming C-C bonds are one of the most important tools in the synthesis of fine chemicals and pharmaceuticals. We have already discussed the general mechanism these palladium-catalyzed cross-coupling reactions all share. Here it is to refresh your memory. Today we will discuss another variant of this reaction, the Negishi cross-coupling. As the name implies, it was discovered by Professor Ei-ichi Negishi, who worked at Purdue University in West Lafayette, Indiana. Negishi received the Nobel Prize for his contributions to cross-coupling in 2010. Negishi introduced organozinc compounds as partners in cross-coupling. These are important alternatives to boronic acids and organotin compounds, the nucleophiles in the Suzuki and Stille reaction, respectively. The main difference is that organozinc compounds are seldom isolated because they are unstable and are quenched by water and alcohols, as they are fairly reactive organometallic species. This is a major departure from the two previous reactions, since boronic acids and organotin compounds are isolable and stable in water or alcohols. Actually, the Suzuki coupling almost always requires water to be present. Organozinc compounds are more reactive than boronic acids and often react at room temperature as opposed to elevated ones. Although reactive, they are fairly insensitive to most functional groups and therefore are employable with all sorts of functionalized substrates. The factors which may have limited the application of this reaction are as follows. 1. It is difficult to characterize these species in situ as they are often prepared from other organometallic intermediates. They can't be isolated and are often structurally undefined. 2. We do not have a clear mechanistic picture of the Negishi transmetallation. It is fair to say that a comprehensive mechanistic study has never been published, which is rather surprising. Not understanding the mechanism forces the chemist to screen conditions rather blindly. All this is often a trigger for switching to the Suzuki coupling if possible. However, organozinc compounds can be prepared in a number of ways, and this makes them very practical intermediates. We will highlight a few methods in this tutorial. First of all, just like for Grignard reagents, metallic zinc can react with alkyl and aryl halides to form alkyl or aryl zinc halides. Usually, the zinc has to be somewhat activated to participate. It is usually in the form of a fine powder, often activated by traces of copper or silver. Some soluble halide salts, like lithium chloride, further facilitate the insertion. The reaction works best with bromides and iodides. If lithium salts are used, usually in ether solvents like THF, the species in solution is mainly the zincate form A, which is favored because organozinc compounds are strong Lewis acids. When one carries out the coupling with these mixtures, one must keep in mind their solution structure. It has been shown that in many cases, lithium chloride facilitates the coupling. However, in some cases, it inhibits the coupling and the overall picture is not clear. Another common way to prepare organozinc reagents is by transmetallation from an organolithium or magnesium species. This is a very popular approach. The compound is not isolated and is submitted directly to the Negishi coupling. One tricky aspect of this approach is determining when the transmetallation from lithium or magnesium to zinc is complete. This can be monitored by spectroscopic or special quenching techniques, but it adds a layer of complication to the methodology. Again, one must keep in mind that the lithium and magnesium salt contained in the organozinc solution will affect the cross-coupling to some extent. We should also consider that rather acidic aromatic CH bonds can be zincated directly using the base ZN-TMPCl, or analogous zinc bases, where TMP stands for 2,2,6,6 tetramethyl This development comes from the labs of Professor Paul Noschel, who works at the University of Munich in Germany and is possibly the top expert in organozinc chemistry. An example of this chemistry is shown here. Another breakthrough was reported about a decade ago by Professor Noschel. By using zinc pivalate in the transmetallation, he has been able to prepare air-stable, isolable organozinc compounds, thus facilitating their use in Negishi couplings. The so-called aryl zinc pivalates are actually a cluster composed of an aryl zinc halide plus a lithium halide and magnesium pivalate. Such complexation evidently stabilizes the CZN bond and makes it insensitive to moisture. These intermediates are fully competent in cross-coupling chemistry. Here is a specific example. As we can see, these organozinc derivatives are nice yellow-brown powders which can be handled on the bench. Let's now discuss the conditions for the coupling. sp2 hybridized halides are common substrates, which means aryl and alkenyl halides, or sometimes even sulfonate esters. Alkyl halides can also be coupled, but they require different conditions, as we will explain later on. The functional group compatibility is excellent, and one should only avoid highly acidic groups, which can quench the organozinc derivative. Most solvents can be used, but it is suggested to avoid water and alcohols. Typically, chemists employ THF, toluene, NMP, or DMF, and an NMP-THF combination is very useful. For the choice of the catalysts, the same considerations apply as for the Stille couplings. Usually, a source of palladium-2 precatalyst is used in conjunction with a bulky electron-rich phosphine. Some examples are shown here. Finally, let's spend a few minutes on the coupling of alkyl halides. This requires new methodology, but it can work quite well. Typically, nickel catalysts are used. Once again, these catalysts feature N-based ligands and not phosphines. The field has been advanced substantially by Professor Gregory Fu at Caltech. Not only has he been able to couple alkyl halides in good yield, but he has shown us how to do it enantioselectively. Here is an example. The substrate 1 is a racemate, and in this case, the organonickel compound formed in the oxidative addition rapidly interconverts to its enantiomer via a radical. Therefore, the chiral ligand is the element controlling the face from which the organozinc approaches, yielding an amazing 98:2 ratio of the two enantiomers of 3. The reaction needs THF to form the organozinc compound, but proceeds more smoothly in a mixed solvent rich in dimethyl imidazolidinone, a highly dipolar solvent which allows coupling under extremely mild conditions. Although the catalyst load for these reactions is still relatively high, this methodology is an important extension of the Negishi cross-coupling and is currently the subject of extensive research. Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.